Okay guys, so this is the last video in redox, and it goes along with how redox is useful in the real world. So last week we talked about electrochemical cells, and specifically we talked about a voltaic cell, which is when a redox reaction goes spontaneously and makes electricity. So another type of use for a redox reaction occurs in an electrolytic cell. And an electrolytic cell is another type of electrochemical cell that's different from a voltaic cell. So how is it different? First of all, it's not spontaneous. So this chemical reaction would not happen on its own. It has to be forced. And how do we force it to happen? We use electricity. So the energy transformation here is electrical to chemical. So it's the opposite of a voltaic cell in that way. There are a lot of other differences. So I'm just going to draw an arrow down here. Differences between electrolytic and voltaic cells. So the charges of the cathode and the anode are different. They're the opposite. And if you calculated Gibbs free energy, the signs would be the opposite because one's spontaneous and one is not. And if you calculated the E cell, the cell voltage, those values would also be opposite of each other because, again, one is spontaneous and one is not. There are things that they have in common. So if you think about N-ox and Big Red Cat, those rules still apply. Oxidation still occurs at the anode, reduction still at the cathode. We still have electrons flowing anode to cathode, so that direction doesn't change. So those are things that they have in common. Okay, so let's talk about what the electrolytic cells look like. If the question is about an electrolytic cell, it's usually easy to tell by the picture if it's an electrolytic cell. First of all, the first thing you notice is that the reaction is happening inside of one beaker instead of two. Because there aren't two separate beakers, we don't need a salt bridge. The other big difference in the picture is that up here we have a battery instead of a voltmeter. So that battery is where the electricity is coming from to start the reaction in the beaker. So the battery is necessary for the reaction to go. So one thing we use electrolytic cells for is to take metals and electroplate them or cover them up with a more expensive metal. So we do this a lot with jewelry, where jewelry has like a cheaper metal inside and just the outside of it is plated with something more expensive like gold or silver. Okay. So here's an example of how that works. So I have, what do I have here? I have steel over here, which is the cathode. How do we know what's the anode and the cathode in an electrolytic cell? The only thing we can do is look at the charge of the battery. So, like I said, the charges are opposite. In an electrolytic cell, the cathode is negative. So because this steel is connected to the negative side of the battery, it's the cathode. And because this nickel is connected to the positive side of the battery, that makes it the anode. We still have oxidation occurring here, and we still have reduction occurring here. So what's happening is at the anode, nickel is being oxidized. So nickel atoms are losing electrons and turning into nickel ions. Where do the ions go? They dissolve into the solution, okay? Where do the electrons go? They go through the wire and to the cathode. So that's something that the voltaic and the electrolytic cell have in common. Now, this is something weird. Usually when we do a redox reaction, a different element gets reduced than was oxidized. Here, we don't have that. We have this negative steel bar. So these positive nickel ions that we just made, they're actually going to swim over to that steel bar because positive is attracted to negative. Now, once they get over to that steel bar, electrons are also traveling to that steel bar. So these nickel ions and these electrons, they're meeting back up and they're turning back into nickel atoms. But now they're turning into nickel atoms on top of the steel. So that steel is being covered by nickel. There's going to be steel on the inside and nickel on the outside. So the same element that gets oxidized also gets reduced, but it gets reduced in a different spot. So here's another example of electroplating. So another way you can tell what's the anode and what's the cathode, aside from looking at the batteries, you can remember the cathode, it starts with a C, is always the thing that's getting covered. That also starts with a C. So here in this picture, they give me an object. They give me a key. If there's ever like a weird object in the picture, that's always the thing that's going to get covered. Okay? So I'm going to label my cathode. I'm going to show that reduction is occurring there. And I'm going to label my anode. And that's where oxidation is going to occur. Okay, so what's happening here? I'm starting off with silver metal. Right? So for silver to get oxidized, it has to turn into a positive ion by losing an electron. Okay? So where are those silver ions going that I made? They're going into the water. Where are the electrons going that I made? They're going through the wire and to the cathode. So the same thing's happening here, guys. The key right now has a negative charge. So those silver ions that I made that are positive, they're attracted to the key. So they're going to like move over to the key. So at the key, I'm going to have a bunch of silver ions. I also have electrons going over to the key. They're going to meet back up and they're going to make silver metal. So whatever that key was made out of, whatever kind of cheap metal it was made out of, that literally doesn't matter. Now it's going to be covered in silver. Okay, so NOx met a big red cat. That big still applies. The cathode is always going to be getting heavier. Here we're literally adding metal on top of another metal. So we have more atoms there, it's going to be heavier. Okay. Another example of how an electrolytic cell can be useful is to purify molten salts, which basically means you're taking a salt, you're taking an ionic compound, and you're breaking it back up into its elements. So why isn't this a natural process? Elements would rather be in a compound because they're stable that way. They have a full valence shell. So to take a compound and to make it decompose, that's something that's going to be not natural or not easy to do. But if you put it through an electrolytic cell and use the battery to get that going, that's something that could work. Okay, so if we take a look at what's going on in this diagram, I have NaCl ions. So this sodium chloride, it's bonded to each other, but when we dissolve it in water, it breaks up into ions. Okay, so what's going to happen is the anode has a positive charge, the cathode has a negative charge. The negative ions are always going to swim to the anode. And what happens at the anode? Oxidation. So this chlorine ion is going to lose its electrons, and it's going to turn back into chlorine, the atom, the element. Positive ions always swim to the cathode because the cathode is negative and opposites attract. What always happens at the cathode? Reduction. So these positive sodium ions that were nice and stable, they're going to pick up electrons now, and they're going to turn back into sodium metal. Okay, so we've taken stable things and turned them into unstable elements. Okay, we also see this reaction happening sometimes in an electrolytic cell. They show it happening with water, where they take H2O and they turn it into hydrogen and oxygen gas. So that's again something that wouldn't be natural because water is more stable in a compound than by itself. Okay. All right. So this is just another example, guys, of everything put together. So when you're using your battery in your cell phone, a battery is a voltaic cell. It's a reaction that happens spontaneously to make electricity. When you plug your cell phone back into an outlet to recharge the battery, you're providing it electrical energy to go back in the other direction. Okay, so it's almost like the battery is the voltaic cell, but when then you're charging the battery, you're using the electrolytic cell. Okay. Last thing, guys, and I kind of talked about this at Extra Help last week. When you see the word agent attached to oxidizing or reducing, an agent is something that helps something else. So if they ask you what an oxidizing agent is, you're looking for the thing that gets reduced. You're looking for the thing that gained electrons so that something else could lose them. When they ask you for a reducing agent, you want to look for the thing that got oxidized. So in order for something to gain electrons, something else has to lose them first. So whenever you see the word agent, you just look for the opposite. Okay, see you guys later.